Будьте так добры. Dear colleagues, I'm glad to invite our today's speaker, Gleb Belozerov from the Lomonosov of Moscow State University, and he will tell us about generalizations of Jacobi-Chasles theorems and Graves theorems. Let's welcome.
Thank you. First of all, I want to thank the organizers of this seminar to the opportunity to do this report. My report will be devoted to generalizations of Jacobi-Chasles and Graves theorem. And first of all, I want to remind the definition of family of confocal quadrics in Euclidean space and some properties of it. A family of confocal quadrics in n-dimensional Euclidean space is a set of quadrics defined by the following equation. Here, a1, an are constant, and lambda is a real parameter. Here you can see two examples of families of confocal quadrics in the Euclidean plane and in the Euclidean three-dimensional space. Okay. The family of confocal quadrics has a lot of important properties, but I want to tell you about two of them. Through each point in Euclidean Rn, there pass exactly n confocal quadrics, taking into account the multiplicity. This fact allows us to define a new coordinates by the following way. Let lambda1, lambda n be parameters of confocal quadrics that pass through a point P. Then function lambda1, lambda n are called the elliptic coordinates of the point P. These coordinates was introduced by Carl Jacobi. And orthogonality. At all points of the intersection of two confocal quadrics, corresponding tangent planes are orthogonal. That is, the elliptic coordinates are orthogonal also.
What do you mean by orthogonal? As vectors in, so if we consider these coordinates as vector in Rn?
Yes, if you consider these coordinates as vector in Rn, yeah. Okay, now we can formulate the classical Jacobi-Chasles theorem. It states that at all points on a fixed geodesic on an ellipsoid in n-dimensional Euclidean space, the tangent lines to it are also tangent to n-1 quadrics confocal with this ellipsoid, which are the same for all points on geodesic. Here you can see the illustration of this theorem. You can see black geodesic on an ellipsoid, tangent lines to this geodesic, and all these tangent lines are tangent also to hyperboloid, which is confocal with the ellipsoid. Okay. Recently, Vladislav Kipkala researched the integrability of geodesic flow on intersection of several confocal quadrics. He obtained that the geodesic flow on intersection of n-2 confocal quadrics in Rn is integrable. He used the approach which connected with integrable billiard theory and billiard books. But it turned out that this fact is also true for an arbitrary intersection of several confocal quadrics. More precisely, let Q1, Qk be confocal non-degenerate quadrics of different types in Euclidean Rn, and Q be intersection of these quadrics. Then the geodesic flow on Q is quadrically integrable. Apart from Q1, Qk, the tangent lines to a geodesic on Q at all of its points are also tangent to n minus k minus 1 quadrics confocal with them, which are the same for all points on the geodesic. Okay. This theorem doesn't follow from classical Jacobi-Chasles theorem. For example, we can consider a limit configuration.
May I see the second? May I see the second statement? Apart from the tangent lines,
tangent lines of geodesic are tangent to Q1, Qk, and also they are tangent for one n minus k minus 1 quadrics confocal with Q1, Qk. This theorem doesn't follow from classical Jacobi-Chasles theorem. Indeed, consider the limit configuration of confocal quadrics. One of the limit configuration. For example, spherical coordinates. That is spheres, conuses, and planes. And we see that the curve of intersection of sphere and conus is not geodesic on sphere and conus. So the classical my generalization of classical theorem doesn't follow from classical theorem. Okay, go next. I want to tell you about the idea of the proof of the theorem. To do this, we consider another mechanical problem. Consider a material point movement by inertia in Euclidean space with Cartesian coordinates x1, xn. Let's find the parameters of quadrics of the given confocal family that are tangent to the trajectory of the material point. Let's assume that at time t0, the particle was at a point with coordinates x1, xn, and had a velocity vector equal to x1 dot, xn dot. In this case, the trajectory of the particle is a straight line defined parametrically.
What do I mean by inertia? Without any acceleration, so just
yes, without any acceleration, without external forces, without forces. Yes, without acceleration. Oh, that is classical geodesic flow in Rn. Okay. Okay. In this case, the trajectory of the particles is a straight line defined parametrically. Okay. To find the intersection points of this straight line with the quadric of the parameter mu, we need to solve the following quadratic equation with respect to parameter tau. Okay, but we find all confocal quadrics such that they are tangent to our straight line. So this equation has multiple root. But this equation has a multiple root if and only if discriminant of it is equal to 0. And
how do you define, so what do you mean by discriminant?
discriminant by tau. This equation
Okay,
is
okay.
discriminant by tau, yeah. So if we write this formula, we obtain the following expression below on the slide. At the bottom of the slide, I'm sorry. If we rewrite the last formula, we obtain then that mu, parameter mu, is a root of the following polynomial with coefficients f0, f1, and so on, fn minus 1. Here, fm is a function depending on point velocity vector and parameters of confocal family a1, an. Sigma mk is elementary is an elementary symmetrical polynomial of variable an and so on, ak minus 1, ak plus 1, an. Okay. All these functions are smooth in cotangent bundle on Rn. Moreover, the function f0 is the total mechanical energy of the material point. And these functions have one main property. To see it, we need to rewrite our first
Well, can you say about this property in just in 2 words? What is the property?
Property is the following. Function fi and fj for all a and j commute with respect to n Poisson brackets, not only one. For n Poisson brackets, they commute.
Okay, great.
Here you can see this property. Note that the sum of such Poisson brackets is equal to standard Poisson bracket. So functions f1, f0, fmn minus 1 are first integrals of movement of material point by inertia. But if we consider the intersection of several confocal quadrics, we need to fix some elliptic coordinates. For example, if we consider geodesic flow on ellipsoid, we need to fix first elliptic coordinates. If we consider the geodesic flow on intersection of k confocal quadrics, we need to fix k elliptic coordinates. For example, if we fix coordinates lambda a1, lambda a p, for example, and don't fix coordinates lambda j1, lambda jq, then the standard Poisson bracket on this intersection, if this is the sum of partial Poisson brackets with number j1, jq. So what we know that first integrals fi, fj commute with respect to any partial Poisson brackets, and Poisson bracket on the intersection of several confocal quadrics is the sum of such partial Poisson brackets. So functions f0, fn minus 1 commute with respect to standard Poisson bracket on arbitrary intersection of confocal quadrics. So the functions f0, fn minus 1 are the first integrals of the geodesic flow on Q. It means that this polynomial is constant on geodesic. So any tangent line on any tangent line to geodesic touched n minus k minus 1 common confocal quadrics. This idea of the proof of the theorem. Now I want to tell you about homomorphism classes of intersection of several confocal quadrics. It's interesting question, but we know if we consider three-dimensional Euclidean space and consider two confocal quadrics, so we obtain only disjoint union of several circles and intervals. It's not interesting. So let's consider a four-dimensional case and two confocal quadrics. We consider only compact intersection. It is equivalent to the following. That one of fixed quadrics is ellipsoid. But how can we represent three-dimensional ellipsoid? Note that two-dimensional ellipsoid may be topologically constructed by the following way. We need to consider two regions bounded by ellipsoid, two same regions. And after we can glue this region on the boundary. We obtain the topological space which is homeomorphic to ellipsoid, two-dimensional ellipsoid. And if we consider elliptic coordinates in these regions, then these elliptic coordinates in the region will be correspond to elliptic coordinates on ellipsoid. So if we want to represent three-dimensional ellipsoid, we need to consider two same three-dimensional regions bounded by two-dimensional ellipsoid, and consider elliptic coordinates in each of them. So if we consider compact intersection of two confocal quadrics, the first elliptic coordinates we need to fix because these coordinates correspond to ellipsoid. If we fixed coordinate lambda 2 in any region, we obtain two-dimensional sphere. So if we glue this region on the boundary, we obtain two-dimensional spheres. But it is homeomorphic to direct product, null-dimensional sphere and two-dimensional sphere. Okay, now fixed first elliptic coordinates and the third elliptic coordinates. What we obtain? In any region, we obtain the cylinder, and after the gluing, this cylinder will be the cylinders go to the two-dimensional tor, but two-dimensional torus is homeomorphic to direct product of circles. Okay, but if we fix lambda 1 and lambda 4, and any region, we obtain two-dimensional disks. And after gluing, we obtain two-dimensional spheres. That is two-dimensional sphere and multiply by null-dimensional sphere. So in each of this example, we obtain direct products of spheres, and it turns out that it is true for an arbitrary intersection of several confocal quadrics. If the intersection of confocal quadrics is compact, then it is homeomorphic to the direct product of spheres as M1 as Mk. M1 and Mk depends only types of quadrics of intersection. But if our intersection is non-compact, we need to add to this direct product disk of dimension L, where L is also depend only of quadrics of intersection. After the theory, my scientific advisor Hans Timofeyevich Fomenko assumed that this fact is also true for Minkowski spaces and for the spaces of constant curvature. And we proved the generalizations of Jacobi-Chasles theorem for these spaces. I remind you that a family of confocal quadrics in Minkowski space RPQ is a set of quadrics defined by the following equation. Here, A1, AP, B1, BQ fixed numbers, lambda is a real parameter. Here you can see the family of confocal quadrics in Minkowski space R21. Remark that this definition of family of confocal quadrics is quite reasonable because Q signs plus we change to minus, or Q signs minus we change to plus. So it's a reasonable generalization of family confocal quadrics. But what is confocal quadrics in sphere, in standard sphere, and in Lobachevsky plane? I'm sorry, I forgot to formulate the generalization of Jacobi-Chasles theorem for Minkowski plane, but here you can see it. Now, how can we obtain the definition of family confocal quadrics in two-dimensional sphere? Denoted by this the standard spherical distance.
Excuse me, in the equations there are all pluses, right? So I mean in the
yes, all
yes,
minuses,
in the,
minuses.
No,
all
I
minuses.
mean in the numerators.
Yes. All in the Euclidean we have Euclidean case we have all minuses, and the Minkowski space we have P minuses and Q pluses. Okay, can I continue?
Okay.
Mm-hmm. Okay. Let's define quadrics on the sphere. What is quadric? What is quadric? We can go by classical way. We can fix 2-point P1 and P2 on the two-dimensional sphere and some positive real number L. An ellipse on two-dimensional sphere is a set E, which consists of all point x on the sphere, such that distance of x p1 plus distance x p2 is equal to L.
Excuse me, am I right that stereographic projection takes quadrics on the sphere to quadrics on the plane?
No, if we consider stereographic projection, we these quadrics will be curves of order 4, not order 2. So ellipse on the sphere is a curve of order 2 of order 4 on the plane.
Okay.
Okay. let's define a hyperbola. Let P1, P2 be 2 points on the two-dimensional sphere, and lambda is a non-negative number. A hyperbola on the sphere is a set of the all point x and sphere such that modulus of distance or modulus of difference between distance xp1 xp2 is equal to L. Note that the distance between points x and p is equal to p minus distance between x and minus p. So a hyperbola on an ellipsoid is or hyperbola on the sphere is the joint union of two ellipses.
Okay.
And now we can formulate the family, the definition of the family of confocal quadrics. It's turned out that a family of confocal quadrics on the sphere is a set of curves obtained by the intersection of the sphere with the cones of the one-parameter family. Here, A is a constant in interval 0, 1, and the family is the following. Here you can see the family of confocal quadrics in two-dimensional sphere. Using similar approach, we can give a definition of the family of confocal quadrics in the Lobachevsky plane. We obtain the following family of cones, but these cones lives in three-dimensional space, and Lobachevsky plane we consider as in model of hyperboloid.
Okay.
We consider in hyperboloid model. Okay, and using this formula for dimension 2, we can generalize corresponding definition for an arbitrary dimension. A family of confocal quadrics on the sphere Sn standardly embedded in Rn+1 and Rn+1 is a set of surfaces obtained by the intersection of the sphere with the cones of the one-parameter family. Here A1, an-1 are fixed numbers, and T is a real parameter. A family of confocal quadrics in the Lobachevsky space Ln standardly embedded in Rn1 is a set of surfaces obtained by the intersection of Lobachevsky plane, Lobachevsky space with the cones of the one-parameter family, which is given by the following formula. Here, A1, an-1 fixed numbers, and T is a real parameter. So, the generalized Jacobi-Chasles theorem for these spaces is true, and it states that if Q1, Qk be non-degenerate confocal quadrics on the sphere or on Lobachevsky space of different types, and Q is B is the intersection of these quadrics, then the geodesic flow on Q is integrable, and the second part of the theorem also are the same as for Euclidean spaces. Now I want to tell you about another generalization of this theorem for mechanical system with integrable potential.
Excuse me. In our seminar, we are very interested in some properties which are called G and K properties. So roughly speaking, we're interested in properties when um, uh, through any point, for any endpoints, we can choose some K so that so that the event any so that the event some k points belong to a curve or surface is codimension 1. For example, for k equal 3, it's a circle. It's a line. For k equal 3, it's a circle. And we can do further algebraic geometry. And also we are very interested in, I would say, non-integrable properties when it also may depend on the other points. So actually, this is some mm, algebraic geometry maybe, but we're interested in how it is related to mechanics. So you may ask Igor Nikonov, and he is also doing G and K. He was one of yes, and
Thank you.
yes, and just keywords: non-integrable G and K properties.
Integral
G and K properties.
G and K properties.
Yeah. Okay.
Thank you. Thank you. Okay, and now I want to tell you about another integrable generalization of the Jacobi-Chasles theorem for mechanical system with integrable potential. Let us consider the motion of material point in Rn under the action of some smooth potential V. We will follow the method described by Kozlov. That is, we will look for additional first integrals of the problem in the following form. The first integral G0 is equal f0 plus v, g1 equals to f1 plus f1 small, and so on, where fi functions which depend only variables x1, xn. The condition of commute that is passing brackets of gi and g0 is equal to 0 leads to the following system of differential equations, which is solvable locally if and only if potential V satisfies the following system of equations.
And what is the method?
Method. We know first integrals of the problem without forces or without potential for the system where point moves by inertia. And now we want to add some potential V. And we would change first integrals of our system by the following way. We want to add to this to first integrals of our classical system some functions which depend only variables x1, xn, only coordinates in Rn.
So it's like in differential equations, we may undefined coefficients. We may perturb it.
Yes. And yes, we want to find such integrable potential V, with such function V, which allow us to write additional first integrals by the following way. Yes. F1 Fn minus 1 is some function we don't know here. Okay, and we obtain the following differential equations, the following system of differential equations. You can see some here. And what interesting I can I can tell about this system. For the if we satisfies this system of differential equations, then functions g0 and so on, gn minus 1, commute with respect to any partial Poisson brackets. So if we consider the geodesic flow with potential V that satisfies this system of differential equation, this mechanical system will be integrable on any intersection of several confocal quadrics, on any intersection. Here you can see this theorem. Let a family of confocal quadrics be fixed, and let V be a smooth function that satisfies the following differential equation in the elliptic coordinates. Then the problem of the motion of a material point on the intersection of several confocal non-negative non-degenerate confocal quadrics in this family in the presence of the potential V is square integrable. So we obtained a new generalization of Jacobi-Chasles theorem for system with potentials. Here you can see some examples of such potentials. The first of them is Hooke potential. The second was introduced by Valery Vasilievich Kozlov. And moreover, this equation has a common solution, which can which can be written by the following formula. Here, f1, fn are arbitrary smooth functions. Okay, now I want to tell you about another generalization of another generalization of another fundamental theorem. And to do this, I want to formulate one problem. Okay, we put a loop on the ellipse, put a pencil inside the loop, and pulling it to the limit, draw a curve. What is the resulting curve? Is a question for you. How do you think? Okay, I can say the answer. We obtain the ellipse with the same foci. So if we put a loop on the ellipse, put a pencil inside the loop and pulling it to the limit, draw a curve. Then this curve is the ellipse confocal with given. This is Graves' theorem. Graves is a British bishop, and he proves this fact in 1841. So this fact has an interesting generalization for an arbitrary dimension. And to do this, we need to discuss some basic facts about integrable billiards. Consider the geodesic flow on ellipsoid. If the smallest semi-axis of the ellipsoid is directed to 0, then the geodesic flow will transform into a billiard system inside the ellipsoid of a smaller dimension. Here you can see this transformation. Geodesic flow, geodesic on ellipsoid go to the billiard trajectory inside a region bounded by an ellipse. Moreover, the following theorem is true. The billiard inside an ellipse is integrable. All straight sections or their extensions of any of an arbitrary polygonal trajectory of this system touch a common quadric which is confocal with the boundary. Here you can see the illustration of this theorem. If we consider the trajectory of billiard bounded by ellipse, then all parts of this trajectory, all their extensions, will be tangent to a confocal ellipse or confocal hyperbola. Let us consider this. Let us consider this system more precisely. Let D be a domain bounded by an ellipse, and M4 is a phase space of this system. M4 is not smooth manifold because of reflection of the billiard body, but M4 is a topological manifold.
Does it have anything to do with altar billiards? There is a very popular theory of altar billiards.
I'm sorry, what billiards? Alto billiard.
I mean, внешний бильярд — это когда вы берете точку.
Да, понял. Auto billiards. Да. It's interesting, but I don't know connection between no, I don't know connection between this theory or that is theory of confocal billiards and theory of auto billiards. I don't know connection between them, but it's interesting. Thank you. Auto billiards. Okay. In the smooth parts on M4, there's a well-defined differential forms alpha and omega, where P1 and P2 are conjugated momenta to elliptic coordinates lambda 1 and lambda 2, and form omega dp1 dp lambda dp1 wedge dp lambda dp1 wedge dp lambda 1 plus dp2 wedge dp lambda 2. In Cartesian coordinates, the additional integrals lambda, that is cosmic parameter, can be written by the following formula. Here is the parameter of caustic. Okay, and now we can use construction of action variables to prove graph theorem. If we fix two first integrals of our system, that they are energy and the caustic parameter. In phase space, we obtain two-dimensional surface. If the parameter of the quadric less than b, we obtain two-dimensional torus. And now consider two cycles on this torus. projections of these cycles you can see on the screen, gamma 1 and gamma 2. Okay, let's calculate the integral of alpha over these cycles. What we obtain? For cycle gamma 2, we obtain the length of the caustic multiplied by h. But what we obtain if we calculate this integral for the cycle gamma 1? It's well known that such integral doesn't depend on if two cycles gamma 1 prime are homologous on Tor, then integrals over them are equal. So the integrals over gamma 1 is the integrals over gamma 1 prime on the left or on the right picture. Moreover, the point L maybe point L is arbitrary. So if we calculate the integrals over the cycle, we obtain the sum of lengths LA, LB minus arc of arc AB, less arc AB. And this expression doesn't depend from the point L. So if we add to this expression the length of caustic, we obtain then the sum of LA, LB, and greater arc AB is constant. But this sum doesn't depend from point L. So we obtain Graeff's theorem. Note that this theorem is true not only for ellipses, but also for hyperbolas and parabolas. Here you can see the illustration of this theorem for these cases. Okay. Now we want to generalize this theorem. To do this, we need to consider billiard inside an ellipse. It turns out that the billiard inside an n-dimensional axis ellipsoid in n-dimensional Euclidean space is integrable. Moreover, all part or their extension of any arbitrary polygon trajectory touch the n-2 quadric or n-1 quadric caustic that is confocal with the boundary ellipsoid. So we can use similar construction and we obtain the Staude construction of an ellipsoid. Okay, how? Okay, let's explain this construction. Consider ellipsoid given by the following formula. Here, a greater than b greater than c. Consider the thread of the length. Thread of length 2 square a plus square root a minus c minus square root a minus b. Let f be a fixed point which coordinates satisfy these properties. X squared divided by a minus c is equal to 1, y and 0 is equal to 0. P1 moves along hyperbola given by the equation x squared divided by a minus b plus z squared divided by c minus b is equal to 1. Y equals to 0. P is thread tension point. Point P2 moves along ellipse, which given by the formula x squared divided by a minus c plus y squared divided by b minus c is equal to 1 and 0 is equal to 0. And G is fixed point, which coordinates satisfy the following equation: x squared divided by a minus b is equal to 1, y and 0 is equal to 0. Then point P will be move along the ellipsoid, along the given ellipsoid. And this construction can be easily proved using action variables. And I and my certificate advisor Anton Timofeyevich Fomenko proved the multidimensional construction of an ellipsoid using this graph. To construct the ellipsoid given by the following equation, consider an inextensible thread of the length 2 square root of a1 plus square root an minus a1 plus minus a n minus a square root of a n minus a n minus 1. Let f0 and g0 be its endpoint. We will fix its point in the location specified in this table. F0 is point. Point f1 moves along the hyperbola, and so on. Fn minus 1 moves along this quadric, n minus 2 dimensional. P is thread tension point. Point G n minus 2 moves along 2n-dimensional quadrics, and so on. G0 is a fixed point. Then point P will be moved along the given ellipsoid. So note that this construction only for ellipsoid using some points in Rn we construct ellipsoid, but we know that the Graves theorem states that we can construct confocal ellipsoid by the given ellipsoid, and we find the generalization of this theorem. For example, if we consider ellipsoid, if we consider the given small ellipsoid, consider focal hyperbola. Focal hyperbola is curved given by the equation x squared divided by a minus b plus z squared divided by c minus b is equal to 1. And consider the thread. The left point moved along the focal hyperbola, and the right point is a tension point. So this point will be moved along some confocal ellipsoid. So this construction is a generalization of classical Graves theorem. And such generalization also true for arbitrary dimension. So that's all, and thank you for your attention. I'm ready to answer your question.
Okay, thank you very much for a very nice talk. Are there any questions or comments? Any questions or comments? Okay, so I think we will be able to discuss it later. So it is recorded. Thank you very much again.
Thank you.